This podcast is brought to you by LMU Munich.
Okay, folks, welcome back after lunch. So this is the second installment of my lectures where I'll switch gears from one dimension and go to 2+1. And in a sense, this is how I first got interested in ADS-CFT. There was a little bit of a gap actually before I really started to work on this. But the main reason I wanted to talk about this work was that I think it's one very nice example where you can see a very close connection between answers that come out of traditional tools of condensed matter physics, such as the Boltzmann equation, and results that come out of ADS-CFT. Okay? So the motivation for this work was actually in high TC, but just a few useful references. Primarily, we're going to talk about a problem of transport actually in a bosonic problem, not in a high temperature superconductor. And so this is the original work by Fisher and company on the Bose Hubbard model and its connection to the superfluid insulator transition. A lot of the technology that I'll be employing in this lecture was actually developed by Subir and also his student at the time, Kedar Damla, for looking at finite temperature transport near quantum critical points. And there's also a few nice chapters in Subir's book that are related to this problem. Okay? So as I said, my motivation for looking at this actually came not from a bosonic system, but was actually in relation to high temperature superconductivity. And there's been some very nice experiments done on the so-called Nernst effect. Okay? And the Nernst effect is a little bit like a thermal analog of the Hall effect. Okay? Nothing quantum in this. We're not looking for kind of discrete plateaus or anything like that. But basically, you take your piece of high temperature superconductor that's some quasi two-dimensional material, and you apply a temperature gradient along one side. And what you want to do is to measure the so-called Nernst effect, which is the generation of a transverse voltage. Okay? And one way to understand this is that in a superconductor, in the presence of a magnetic field, you have vortices that flow under the action of this thermal gradient, and by the Josephson effect, if there's a phase difference due to the motion of these vortices, you'll get a voltage generated across the sample in the transverse direction. Okay? So it's conventional to define this so-called Nernst coefficient, which is the relation between this transverse electric field and the temperature gradient you apply, and it's conventionally normalized by this factor of B. Okay? And one of the things I'll try and unpack in a moment is that, and I'll do this on the blackboard, it turns out that in order to understand this, you can actually recast it in terms of the transport coefficients. And in a sense, this is where connections to ADS-CFT come in, because holographic methods are very powerful in computing transport coefficients. And in particular, the nature of solving this problem is rather different than in condensed matter physics. And I think it offers many opportunities to see things that are rather hard using conventional tools in condensed matter physics. So in relation to the high TC materials, here's just an incredibly simplified cartoon just for the purposes of this discussion. I mean, basically, you're changing the chemical composition of some material, usually represented by this symbol X to represent doping, and going from some antiferromagnetic insulator, a Mott insulator, to a superconductor. Okay? And part of the thing that makes high temperature superconductors very difficult to understand is in some sense the fact that these parent compounds, okay, are very strongly interacting systems. Even the insulator is interesting. Okay? So a Mott insulator, in contrast to a conventional band insulator, as you'd learn about in most solid state courses, is insulating by virtue of interactions, okay, not because you filled up a band. Okay? And so in essence, when you try to understand superconductivity, what you're saying is, can you take this incredibly correlated state of matter, change its chemical composition, and somehow understand how superconductivity emerges out of this state? Okay? And we've heard some talks earlier about interesting phenomena going in this regime, connected with what's called strange metallic behavior, okay? And in particular, these Nernst experiments also show interesting signatures in this regime. And in particular, they show these signals way above the transition temperature, okay? So this is actual data taken from lanthanum, strontium, copper oxide as a function of doping. This is the superconducting dome. And what you see is that this onset of this Nernst signal is occurring way above TC, okay? So the point is that what this is somehow telling you is that a high temperature superconductor is gearing up to be a superconductor well in advance of TC, okay? So the explanation I gave for the appearance of this Nernst effect in a conventional superconductor was due to a flow of vortices, okay? Here you're above the transition temperature, okay? So you're not actually a superconductor. So how do you describe this region, okay? And so one of the things we keep hearing about in relation to CFTs is that you don't necessarily have some quasi-particles that you can kind of latch onto, and you have this very strongly interacting state of quantum matter that is very difficult to know how to go about describing, okay? And so the motivation for the work that I'll describe was actually just to say, okay, in a high temperature superconductor, this is clearly a complicated problem. What can we do to shed light on these transport coefficients and perhaps the Nernst signal in a slightly simpler setting where you might hope to get a handle on these strong quantum fluctuations, okay? So what we actually chose to do was to look at this problem in the Bose-Hubbard model, okay? But before doing that, let me just discuss these transport coefficients so we see what we actually need to chase, okay? Let me just, should I just turn this off? Is that probably the best way? It's okay, I don't need it for a little while. I'll turn it off. Okay, so let's just have a look at how we see what transport coefficients we actually need. Yeah, question?
Is there a picture of how the Nernst signal can come about if there's no notion of vortices, just in terms of like charged quasi-particles?
Well, actually, so very good. So I skipped over that. So in this region, there's actually been a lot of work done, actually. So there is a huge body of literature done by Shivaji Sondhi and Ido Ishushkin, using essentially time-dependent Ginzburg-Landau theory, okay, to understand a kind of mean field description of the Nernst effect, okay, that actually works rather well, okay, in the appropriate regime. Now, one subtlety that's actually raised when you do these calculations, okay, is that if you look at the Nernst formula that I wrote down, it involves thermoelectric transport coefficients, okay, and this is what I'll talk about, because we're applying a temperature gradient, looking at a voltage, okay, and we'll relate that to transport, but it means you're looking at electrical response in response to temperature gradient or vice versa. When you analyze this diagrammatically using a Kubo formula, it turns out to be very complicated, okay, and it's complicated by virtue of something known as magnetization subtractions, okay. And very crudely speaking, it's because if you apply temperature gradient to a sample in a magnetic field, basically your magnetization varies slightly as you go across the sample. And you can imagine there's currents in the bulk of this sample that don't quite cancel out. And so if you do it diagrammatically, in order to verify the so-called Onsager relations that demonstrate that the heat flow in response to an electric field is related to the electrical response in a temperature gradient, you have to use these magnetization subtractions. So that was something computed by Bert Halperin and Nigel Cooper. And so the bottom line is, when you do that subtraction in a Kubo formula, you can actually understand a lot of the Nernst data, okay? What we were interested in for this work was actually what happens in relation to this kind of strongly fluctuating regime where you go from a Mott insulator to a superfluid, trying to get out some universal response.
I'm still confused about a more naive question.
Okay.
Does it only happen if there's some like nearby superconductivity?
I mean, there may be other ways in which you could get a thermoelectric response which would look like a Nernst signal, but it wouldn't be a Nernst response, meaning...
Can that mu be non-zero, I guess is the question.
Yeah, so I mean, if you have other mechanisms for generating a thermoelectric response, okay, then yes. But this is specifically in relation to the superconducting contributions. Yeah.
I guess I'm confused about, like, if you're doing an experiment, how you tell which one it is if you measure that new.
Well, because in a sense you have to have a theory and actually subtract off any other contributions associated with normal state carriers. Yeah. Yeah, sorry, I hadn't realized that's what you're asking. Okay, this actually isn't turning off, is it? Okay, we'll see how that goes. Okay, so let me try and zoom in then on the transport question, right? So if we look at these transport coefficients, okay, which rather remarkably when we look at in Boltzmann, we won't actually have to get our hands dirty with any of these magnetization subtractions I talked about, okay? Okay, so this is how you would normally denote the transport coefficient, conductivity. This is thermoelectric tensor. This is thermal conductivity, and we're placing an overbar on it to point out the fact that actually usually thermal transport is defined in the absence of any particle transport, okay? And so it's conventional, well, actually it was notation suggested by Sue Beer to actually denote this quantity as written as kappa bar, okay? So in addition, this alpha twiddle is related to the heat response in an electric field, okay? And by the Onsager relations, this is supposed to be related to temperature times alpha, okay? Now, as I was saying before, if you do this diagrammatically, that doesn't drop out automatically, and you have to do some legwork to change the microscopic definition of your currents so that they satisfy the Onsager relations. Here, in this Boltzmann way of doing things, it's actually an important non-trivial check to make sure that these things are equal, and it's something we did. And in this context, what it will show is that there's rather interesting connections between transport of heat in these systems that are somehow related to Lorentz transformation arguments for electric and magnetic field, although you can't use Lorentz transformation arguments when you're talking about temperature gradients, usually, okay? So fine. So maybe today I'll figure out how these actually work. No. No. Third time. Okay. Okay, so these Nernst experiments, as I said, you're measuring this Nernst coefficient, okay? And because you're measuring a voltage, right, this is an open circuit measurement rather than a closed circuit measurement. And so what you want to do is you want to impose the fact that you're looking at this in the absence of any electrical transport, okay? So if you set that equal to 0, the top line gives you the following. And if you rearrange that then for the electric field, you get this. And so if you now expand this out, and remember that these in general are matrices, okay, so this is alpha xx, alpha xy, okay. Okay, and then you have to take the inverse of this and divide by the determinant, which I'm sure you can work out. The point is that if you want to look at what this quantity EY is, okay, then relate it to the temperature gradient, okay? It looks a little bit complicated, but you find that EY over minus grad T, okay? And this denominator factor basically comes from working out the determinant of the transport part, the conductivity part, right? And then you've got to cross-multiply these matrices. Oops. Sorry, I probably divided by that. I don't think I need that. Okay? So the upshot is, okay, if you want to look at Nernst, okay, it looks something like this, right? So in general, you've got sigma xx, sigma xy, alpha xy in this formula, and what it's saying is to understand these types of experiments, actually you have to understand this full set of thermoelectric response coefficients. And in particular, in the way we've tried to set the problem up, or we will do in a moment, we're asking what are the forms of these transport coefficients close to a quantum critical point in 2+1 dimensions. Okay? So one simplifying assumption we can make, and it will be relevant to what we're going to do, is just to assume that we have some particle-hole symmetry. Okay? So if you're imagining that you're going to try and describe some Lorentz invariant situation where particles and holes appear on an equal footing, or particles and antiparticles, then we can cross out this sigma xy term, okay, which is basically saying the Hall effect vanishes because if you've got particles and holes moving under the action of an applied electric field, then they're going to move in opposite directions, okay? But if you apply a magnetic field, they're going to move in the same direction, but since one carries a plus and one carries a minus, they're going to give you no electrical transport in that direction. And so when the dust settles, what it says is that in order to understand this Nernst coefficient, okay, it's actually relatively simple. Okay. You need to know alpha xy in a magnetic field, obviously, but also sigma xx in a magnetic field. And in fact, with the benefit of hindsight, okay, this is actually a rather stupid place to go looking for the Nernst effect, because typically electrons in magnetic fields execute cyclotron orbits, which means that sigma xx vanishes in a clean system, and that the Nernst coefficient diverges. Okay? Nonetheless, the assumptions that we will make actually turn out to be very useful for looking at what the form of alpha xy is, and also seeing that there's also non-trivial thermal conductivity. Okay? So this is in some sense a kind of entry point to looking at the quantities behind the Nernst signal, but to understand Nernst, you're going to have to do a little bit more. Okay? And I'll come back to that at the end. Okay? So are there any questions so far? Okay, so what model are we going to look at this in? Okay? So we had a very nice talk by Subir, where he started out talking about the very nice experiments on Bose Hubbard, and this is in fact a very nice arena in which to ask this kind of question. Okay? Basically because, as Subir pointed out, the field theory describing this transition is a very paradigmatic field theory that's in any textbook on quantum field theory, namely lambda phi to the 4. Okay? So it's some complex interacting scalar field, complex field, and in most books on quantum field theory, you're interested in things like critical phenomena. Okay? But there's very little devoted to any discussion of transport in this kind of setup. And so, in fact, starting to ask these questions was, I think, actually largely due to Subir, actually, in a more conventional condensed matter type of language. But it's this kind of logic of trying to understand paradigmatic results for paradigmatic models that eventually leads to breakthroughs. Okay? So explicitly, we're going to look at this in connection with this Bose-Hubbard model. Okay? And also, it's probably worth pointing out, I mean, the Bose-Hubbard model, when it was written down, or at least the phase diagram was written down, let's put it that way, in the paper by Fisher and Company. One motivation for this was actually in connection with superconductivity, right? So even though they're bosons, not fermions, the logic was somehow that if you have some thin film superconductor where you deposit metal on some substrate, then it's known that you can make such systems go through superconductor insulator transitions as you make the film thicker. Okay? So as you make the film thicker, these blobs will grow, and Cooper pairs will be able to tunnel between these islands, and so at a critical thickness, the material will undergo bulk superconducting transition, and so this was written down in relation to these kinds of problems as an effective problem of Cooper pair hopping. Okay? So in relation to thin films, normally you would have a disordered Bose-Hubbard model. Okay? Here we're just going to consider a clean, perfect Bose-Hubbard model and ask about its transport properties. So as Subir also mentioned, I mean, you know, this has kind of been the focus of huge amount of activity over the last few years, thanks to making these things in cold atoms. And the point is that the phase diagram of this Bose-Hubbard model, in mean field theory at least, okay, looks something like this. Okay, if you look at the problem, say in 1D, these lobes get somewhat sharper. Okay, but let's just look at this in kind of mean field theory. So these are these Mott-insulating lobes, okay, where you have either 1 particle per site, 2 particles per site, or 3 particles per site. And as you increase the hopping, the atoms want to kind of hop around, and they go from this Mott insulator, where there's perfect 1 particle per site, okay, to a superfluid, where they're all bombing around and they're phase coherent. Okay? And Subir also talked about the nature of this transition as you go between the Mott insulator and the superfluid. And one thing he stressed was that quite often you can describe these transitions by a relativistic field theory. Okay? And since I've drawn the phase diagram, it's worth pointing out that in general, the transition from these Mott lobes to the superfluid is actually non-relativistic at these points. Okay? So here, if you go through this tip of the Mott lobe, okay, you have a kind of particle-hole symmetry or particle-antiparticle symmetry, because the energy cost to adding a particle or removing a particle is basically controlled by the distance you are away from this boundary. So if you transit through the middle of this lobe at constant density, then you have this symmetry, and your theory is Lorentz invariant with a dynamical critical exponent 1. Okay? If you go through these regions, the dynamical critical exponent is 2, and in particular, actually, it could even be an interesting area to look at ADS computations, just because I don't think anybody's seriously looked at what happens if you change the dynamical exponent. It might be something straightforward to do just from the work of Sean and Subir. But in any case, the most accessible point, at least my traditional condensed matter tools, is to just focus on the Lorentz invariant transition that is described by this theory that was written down in the previous lecture of a complex scalar field. Okay? Okay, and the basic question then is, what are the thermoelectric response coefficients of this system? Okay, so applying temperature gradients, looking at electric heat transport, magnetic field, so everything is what you want to try and understand. And in particular, as I'll point out in a minute, I mean, you also have to understand the problem generically at finite frequency. Okay, so one problem, of course, in trying to understand these things is that what you're really asking is, how do you compute it at the critical point? Okay, that's where you're going to hopefully get some non-universal features. But the problem is that's clearly a difficult problem to set up. And so it's going to, one, require a slightly more tailored program to solve this than a simple diagrammatic calculation. But there's also another aspect that was pointed out by Subir, that if you're close to a quantum critical point, where the only scale in the problem is temperature, then your electrical conductivity is actually a function of omega over t in general. Okay? So there'll be some dimensionful prefactor that I'll unpack in a moment. But basically what it's saying is the AC conductivity, I should draw that a little better, it doesn't necessarily go to 0, is some non-trivial function of omega over t. Okay? So what that says is that if you do a computation at t equals 0, okay, you may actually be probing the result out here in this so-called collisionless regime. Okay? And so, in fact, the early papers looking at this actually did that. And so they computed a value for this conductivity, okay, which was actually the result out at infinity. Okay? Now, it's still potentially an interesting number within the framework of this problem, but it's not the DC response. Okay? So this is what's referred to as the hydrodynamic regime. Okay? And so what it says is that in order to get at this, you're going to have a formalism that allows you to work at finite temperature and also access, preferably, the real-time dynamical response so that you don't have to analytically continue back from imaginary frequencies. Okay? What it says is your usual way of doing path integrals, which are in imaginary time, are not going to be particularly helpful for this problem. You might be able to do it, but it's not clear at the outset. Okay? So what Subir and Kedar did was to rather set up a kind of Boltzmann equation where you could compute these conductivities and compute this crossover function for the case of the electric response. And so what we're going to be interested in ultimately is trying to generalize those calculations to include both magnetic fields and temperature gradients. And in fact, it actually shows, well, interesting results that do have a direct conversation with the results that come out of the ADS-CFT correspondence. Okay? Sorry?
Does it have to approach a constant at large frequency?
I don't know. I just meant that it didn't have to be non-zero. Maybe Subir knows more examples of the value at infinity. It's been computed both within the Epsilon expansion, I think, and 1 over n as well. I mean, generically...
Right, that's the value at infinity.
Yeah. Okay. Okay, so fine. So let's press on. Okay. So what was pointed out then is that if you kind of write the conductivity slightly more carefully, okay, including the dimensional factors, okay, so this is h bar omega over kt. So even though you have some scaling, I mean, obviously you have to have the correct dimensionality out of the front as a prefactor, and this generically depends on the scaling dynamical exponent. Okay. Oh, sorry. So this is kt over h bar c, d minus 2 over z, sigma of h bar omega over kt. I see. Yes, okay. Very good. Yeah, actually, it is a pain to do that, actually. You know, sometimes these factors of h bar and kb actually are useful, right, in actually trying to understand formulae. I think for the purposes of this talk, I'll skip over this. But actually, just writing down this form is instructive, okay? Because one of the problems we had when we first looked at this problem in electric and magnetic fields is actually if you just write down scaling forms for the arguments, you can actually get a lot of intuition about what the potential answers could be. Okay? The problem comes if you've got, say, a problem in a magnetic field and you relate this in a scaling form to the temperature, you've still got to convince yourself whether it goes with the magnetic field or inversely with it. So it doesn't actually pin things down, so you still need to do some physics. But it can be very helpful for just unpacking the global features of the transport properties. Okay? So even if you're doing ADS-CFT, don't be afraid to do very cheap calculations just to guess the answer in advance. Okay. So fine. So we need this real-time approach, and I should say that the charge here, Q, is going to be 2e for these Cooper pairs. I'm going to skip the stuff on dimensional analysis. We can always come back to it. So now the name of the game is that, you know, obviously we want to try and understand the form of this conductivity, but the problem is that we have to do it in the vicinity of the critical point. Okay? And Subir, oh, sorry, there's a question. Yeah. But if it depends only on omega over t, it means you can never look at any quantity that has dimensions. So if the physical quantity has dimensions, then it has to be some dimensionful prefactor times omega over t. So for example, in the quantities we were looking at yesterday in relation to the neutron scattering, what we saw scaling in was temperature times the dynamical structure factor, and that had scaling as a function of omega over t. Okay? So in general, there is some dimensionful prefactor that stands out in the front, but close to a critical point, the only dimensionful quantity is the temperature, and so it just ends up as some power of the temperature to the dimension.
You are going to set d equal to 2.
So I'm going to set d equals to 2, but again, the reason for these kinds of scaling arguments is sometimes then you can get beyond just d equals 2, say. And also, for example, the stuff that Subir and Sean did, my understanding is a lot of those results do specifically relate to 2 plus 1 dimensional Lorentz invariant hydrodynamics. But the generalizations, at least heuristically, how it would go as a function of temperature, you can probably write down just based on scaling. But whether or not you could compute these functions is another story. Okay. Okay. So as I was saying, that the thing that Subir pointed out in the last lecture was that in order to access this non-trivial so-called Wilson-Fisher fixed point, you have to set these values to things. This flows to some value u naught star. This mass is the coefficient that you have to basically tune in order to get to the critical point. So these won't be independent parameters, and they will appear in the Boltzmann equation we write down just because we're trying to keep track of critical fluctuations. Okay? So then for lambda phi to the 4, I mean, the usual thing you do in any textbook on quantum field theory is to use the Epsilon expansion. Okay? I have to confess, even though it is widely used and it is incredibly powerful, and I will demonstrate here that I think it is actually very powerful, I just find it incredibly difficult to deal with conceptually, right? Because your physical quantities are in a particular dimension, and you're doing an expansion around another dimension, and in a sense, that shouldn't be so much of a big deal because the only place it will enter is in terms of the dimensionless prefactors, okay? But nonetheless, it can be a little bit confusing when you mix physical dimensionality, okay? I mean, the dimensionality is important for determining the form of the transport coefficients, okay? Nonetheless, it does offer you a large degree of control of the field theory, and so the point is that above the upper critical dimension you have mean field behavior, and you want to try and descend below this upper critical dimension to include the quantum fluctuations. So if we just jump ahead a little bit, and I will just justify this, but I think it's better just to write down the answer in advance just so we know where we're heading, then if you just unpack this and recognize that h bar is not equal to 1 and just put the 2 pi in the numerator, then the result of Subir was that this sigma of naught could be evaluated. It's some number within the epsilon expansion point 1650 over epsilon squared times 4e squared upon h. Okay, and if you multiply that out, that's 1.037 times 4e squared upon h. Okay, so it's some universal dimensionless number. Okay, so I've actually got rid of the epsilon squared because we're assuming that we're going to work in 2 dimensions and set epsilon equals to 1 at the end of the calculation. Okay, so this resonates rather nicely with what Subir was talking about in the last lecture, is that these prefactors in this conductivity, this is information about these universal amplitudes in lambda phi to the 4. Okay? Now, you wouldn't use an ADS-CFT computation to determine that number, right? Because it's not going to have anything to do with the number that's appropriate for Bose-Hubbard or your experimental system. Okay? Nonetheless, one of the very interesting results to come out of the work with Subir and Sean was that actually all of the transport properties of this model turn out to be related to this quantity. It's not obvious at the outset. And so, in a sense, the value of this number doesn't really matter if you want to compare results between different models. So it will be specific to the model under question, but the links between all the different transport coefficients turns out to be a consequence of relativistic hydrodynamics. And so this will be an important sense in which ADS-CFT is able to help organize interesting questions that are of relevance to condensed matter. Okay? And it's a question what details you choose to focus on and what you don't. Okay? So I should say as well, I mean, this was interesting at the time because experiments on thin films did show conductivity that's close to 4e squared upon h. I mean, they're incredibly difficult experiments to do and to actually determine these universal transport coefficients, but it was interesting that at least, you know, they're in the right ballpark, okay? So fine, okay. So how do you get at these kind of results? So what I said is you want to try and construct a Boltzmann equation, okay? So let me just write it explicitly. For a distribution function, f plus or minus kt, okay? So very crudely speaking, what you're imagining is that you have your interacting complex scalar field. You can expand this in terms of mode creation and annihilation operators, A and A dagger, and this distribution function, let's say f plus, is basically the expectation value of AK dagger AK, okay? So it's clearly has a kind of feeling that it's some kind of semi-classical type description. You're imagining particles moving under the action of an electric field. They're scattering off each other, okay? And one important aspect of this description is that this particle-like picture is in some sense justified within the epsilon expansion and is most simply understood with reference to the Mott insulator, okay? So if you imagined this Mott insulator, okay, there's these particle hole-like excitations around this background, and so you can imagine that, you know, if you come from this Mott insulating side, you're going to approach this transition. In the transition region itself, everything's fluctuating like crazy, so it's hard to think at all. But to the left of this transition, okay, there's a kind of basis of particles, they're scattering off each other. And what you want to do is you want this collision term to kind of reflect the structure of your collisions induced by this lambda 4 interaction, okay? So this collision term has basically been the bane of my existence for about 18 months when I was a postdoc, because it's a mess, okay? It has a very simple interpretation, but when you want to do detailed calculations, it's cumbersome, okay? And I think this is one particular aspect that ADS-CFT is very useful for. On the other hand, if you want these numbers specifically for that model, you have to have a calculational scheme, okay? So ADS-CFT doesn't get around that in my view, okay? So what does this collision term look like? Well, it has to involve this fixed point coupling, so I'm not going to put an asterisk on it, probably just call it U0. So this is this coupling evaluated at this fixed point, okay? It involves an integral over momenta, okay, of a bunch of scattering particles. Okay, and the next factor of 2 plus the d plus 1. I don't quite know why I put it on the right-hand side, but there it is. Okay, so this says that you've got some in and out term that are describing scattering of these particles. You're going to integrate over a bunch of momenta corresponding to the outgoing states. And this collision term is really where all the meat of the problem is, okay? So let me just write it out explicitly, and then hopefully we'll never have to do this again, okay? Okay, and the term F in follows by replacing F goes to 1 plus F. Okay, so let me just kind of expand upon this. It's actually not so bad, but you can start to see how it's going to get a little bit heavy when you want to solve this equation. Okay, I should state that this is an integral equation, okay, integral differential equation for these distribution functions, because this right-hand side, this collision term, involves an integration over momenta. Okay. So what it's saying basically is that, you know, you have some process where some particle comes in, okay, and goes out with some K2 and K3, and there's some interaction between these particles, as you would expect in a Landau to the 4 theory, okay, and these are Bose occupation factors, at least if you didn't apply any electric fields. So the point is there's some probability for being in state K and K1, and then there's an amplitude to scatter into a state K2 and K3, and the 1 plus F represents Bose stimulated scattering. If it was a fermionic Boltzmann equation, this would be 1 minus F. Okay? If it was a classical Boltzmann equation, you wouldn't have these ones. And roughly speaking, there's a factor of 2 here because you've got 2 combinations of plus and minus coming together. This term has both pluses coming together. So there's kind of scattering into state K and scattering out of state K. Okay? So it's very appealing. Somehow it's a classical equation for these distribution functions. The effect of the nonlinear interactions in Landau to the 4 is subsumed into this term. The critical couplings are absorbed into the prefactor, and in particular within the Epsilon expansion, let me just write it down explicitly, okay? The factors are given in Soubert's paper with Kedar. And I didn't state, but these are relativistic particles where the mass is essentially determined by the fact that you're looking at the problem at finite temperature. Okay, so you're close to a critical point, but you're at some finite temperature above it. Okay, and the velocity is d epsilon k dk. Okay, and so the thing that's really helping you out here is this U0, okay, involves epsilon, so the coefficient goes as epsilon squared. And so if you were to look at that within the framework of something like a phenomenological Boltzmann theory, where you had some scattering out of your state with some characteristic time tau, then your time for scattering is going as epsilon to the minus 2, which means that if epsilon is small, this is a long time scale. And so, in a sense, your quasi-particles are living for a long time, thereby, in some sense, justifying this quasi-classical approach. Okay? Okay. So fine. So we've written down the Boltzmann equation, but then, how do you extract transport coefficients? So what you're going to want to do is to write down the natural expressions that, for example, the heat current, or the electrical current, okay, is just going to be obtained by integrating over these distribution functions. Okay, so particles go to the right, holes go to the left, and so you've got a difference of terms. So what is the name of the game then? So the name of the game is to try and solve, in general, this integral differential equation for the distribution function and plug it in that expression, do an integral, and there is your answer. Okay? And it's going to depend on epsilon because f is determined by this equation, which has been written down to take into account critical fluctuations. Now, obviously, you're not going to be able to solve such an equation analytically, or it's not clear you're going to be able to solve such an equation analytically, let's put it that way, because it's such a horribly nonlinear equation. So the natural thing to do is to linearize this equation and to look at linear response transport coefficients. Right? So if you didn't have an electric field, okay, so in the absence of E, what you can demonstrate is that this equation is satisfied with a Bose distribution function, right, as you would expect. Okay? It says if you don't apply an electric field, your system is in equilibrium, so your particles and holes have a Bose-like distribution. Okay? So if you want to look at this in the frequency domain, you've got to Fourier transform. Okay? And so what this suggests is that this is the Bose distribution function. And what you want to do is to add a term describing the departure from equilibrium. Okay? So this is the electric field that's causing the shift from equilibrium. K is the only vector really that's floating around that you can dot into this. And so what it says is the natural thing to do is to parameterize it in this way so that there's a scalar function, psi as a function of k and omega, that you want to try and tease out from this equation. Okay? So in doing that, what you're going to be left with then is a linear integral equation. Okay? Yeah?
Is it totally obvious that the equilibrium distribution for interacting things has to be Bose distribution?
Very good. See, let me just tell you now. So the reason is because this has a nice property that 1 plus f is e to the beta times f. So what that means is when you substitute it into this equation, okay, you know what, it's very good you mentioned that. I forgot, there's a bunch of delta functions. I didn't quite write it out, okay? So you've got, I haven't written them. There's delta conserving delta functions, okay, that k plus k1, let me write it out and make sure I got the conventions right, okay? Okay, so some particles come in with some energy, they go out with the same total energy, the momentum is exchanged, and because 1 plus f, okay, is equal to e to the beta epsilon times f, what it means is that when you substitute it into this equation, you've basically got a string of f's, and provided the energy of the starting state matches the final state, the Bose distribution will automatically satisfy this equation. And in fact, that's another way to state why you need these mode-enhancing factors so that indeed the Bose distribution satisfies it in the presence of interactions.
So that's true for whatever interaction you wrote down, as long as it conserves energy. Right? It doesn't have anything to do with final before. Right?
Well, so, I mean, true. I mean, so here we have an explicit collision term that we've written down reflecting the lambda phi to the 4. But in principle, in a generic interacting theory, this will have some expansion, okay? And presumably the Bose distribution will also have to satisfy the generic interacting fixed point. Okay?
But I think it's just
If it's in equilibrium.
But is it clear that there can't be some other distribution that solves that's stationary, that solves it?
No, that's actually a good question. So, I mean, in principle, this actually cropped up actually in discussions of trying to solve these equations. In principle, there are other functions of energy and momentum, okay? But I think there's some assumption of naturalness in a sense that it has to reduce to the Bose, to equilibrium things in the absence of applied electric fields, okay? So it's a good question, actually. I should look at that more carefully, actually, to check what the most general solution of these equations are, okay? But the basic point is that in equilibrium, you get out what you're supposed to get out, okay? And it's, in a sense, been constrained to do that, okay? So these types of equations can be derived systematically within Keldysh, but, you know, it's quite a heavy calculation to kind of tease all these things out. Okay. Okay, so what do you get then if you do this linearization process? You get the following equation for the departure from equilibrium. okay? So it's some integral equation, a linear integral equation, okay? This comes from Fourier transforming the time-dependent case. If you're only interested in DC response, you can switch this off. And so in general, to understand the finite frequency response in this model, you're going to have to solve this equation for each frequency and then try and integrate it to get the current, okay? Yeah? You can, but the point is that you can derive it from Keldysh field theory in a perturbative expansion in the epsilon expansion. So this isn't, even though I've written it down in a heuristic form simply because it's a Blackboard lecture, this collision term can be derived, okay? In a sense, it kind of has a structure reminiscent of the Fermi golden rule, in which you've got some kind of matrix elements for particles coming in and going out. So within a controlled expansion, this isn't arbitrary, okay? It's not just been written down heuristically. You can derive this term, okay? The question more is perhaps, are you actually going to get anything like the correct answers out of this calculation, okay? And what I will try and ultimately conclude with is the answers you get out of this do in fact match the predictions you get out of ADS-CFT, okay? So within ADS-CFT, you might not have any quasi-particles floating around, but nonetheless, this Boltzmann calculation, I think, is capable of reproducing such answers in situations where you do have some notion of quasi-particles. Okay. Is that okay? I mean, the good book on this is Kadanoff and Bain, where they discuss how to compute such collision terms, okay? So you basically have to take expressions. You know, roughly speaking, I mean, this corresponds to a diagrammatic expansion involving such diagrams, right? We've got some interaction U0, some interaction U0. It's defined within the epsilon expansion. So there's a other class of diagrams that you could in principle write down. But in general, if you're going to do an epsilon expansion, I mean, if you did this for critical phenomena, say, you would write down an epsilon expansion to a number of orders. You might try to do fancy tricks such as Borel resummation, etc., etc. But just to come back to the point we were discussing earlier about dimensional analysis, basically what you know is that the answer is going to have to be something of this form. So this prefactor, right, evaluated, let's say, at 0 frequency, is what we're trying to compute. But it's a dimensionless number. Now, to be perfectly blunt, when I was looking at this problem, even though I have to solve these equations, I wasn't that interested in those numbers, okay? And the reason is I was more interested in what the physical dependence was on the magnetic field, on other parameters, because, you know, we didn't understand what those were. That's what we were chasing. But you have to get these numbers out. Now, the fact that they agree with the ADS-CFT correspondence actually looks rather non-trivial when you do the epsilon expansion, because the results of relativistic hydrodynamics are done directly in D equals 2 plus 1, and the fact that there can be a conversation between these problems is in some sense that this has non-vanishing and non-trivial content, and that it is consistent with more general approaches. Okay. Is that okay? Okay, good. Okay, so let me just show you what these functions f1 and f2 look like, okay? The reason I do this is not because we won't have to look at them in any great detail. It's just that I just want you to kind of have an impression, first of all, just what the functions look like. So I want you to feel my pain. That is exactly what I want you to feel, right? Because I felt it, and when you see the kind of simplifications that can come out, what it shows is one, maybe I could have bypassed that pain, okay? But rather crucially, that you wouldn't see such things unless you went through the pain of computing them, right? So let me just show you, right? So the point is, these were actually computed by Subir and his student Kedar, okay? Absolutely precisely, but they weren't published in their paper. I mean, I'd have written a special edition of the paper to include these things, right? But so I was quite impressed by the fact that they were actually 100% correct and everything was bulletproof, okay? But it's not so much that they're so bad, but when you're trying to deal with this numerically, they're just unwieldy, right? So you've done the integrations over K1, K2, and K3, and so you're left with these non-trivial functions of K and K1. In general, they have integrable singularities, and so F1 is not so bad, but F2 starts to look a little bit more grim. Okay, it involves some products of the Bose distribution functions. These are defined in some other functions involving these polylogarithms, okay, which are functions which usually emerge in integrals over the Bose distribution function, okay? So they're not that bad, right? But on the other hand, it's not exactly a back-of-the-envelope calculation to kind of, handle these things, right? So that's all I wanted to state about those, okay? So let's turn this off. We should never look at such things again. Oh. Okay, so good. How am I doing for time, actually? What time did we start? We started at 5:30. Sorry, I've lost the plot, 2:30. So we've got half an hour. Okay, good. Okay. So fine, okay. So what did they find? Actually, whilst it's... I shouldn't have done that. I could actually show you the result. Let me show you their result. Okay, so this is their results that they computed. Okay, so there's no point in me going through that. Okay, so this is this function. You can see they've worked it out at all the discrete points, and you evaluate this function at the origin, and you substitute it in that formula, and lo and behold, in 2 spatial dimensions, you see that it's this multiple of 4e squared upon h. Okay, so that's a result of a numerical analysis of these linear integral equations. Okay. So now what we want to do is we want to try and understand the thermoelectric properties, where we also start to include magnetic fields now. Okay? And so this makes the problem somewhat more challenging, because you see in that equation we have a longitudinal shift of the distribution function. Okay? Have I managed to break this? It looks like I might have. No. So in general, in crossed electric and magnetic fields, we're going to have to keep track of both longitudinal and transverse shifts of the distribution function. I was warned that that might happen. Okay, so at least. Is there any way for me to stop this process, or does it just... Let's wipe all of this off as well. So, okay, so basically what we're going to start off with is, well, first of all, let me state one thing, okay, that I forgot to mention. So one aspect of this is the fact that we've got a finite conductivity at all is actually, or rather Subir and Kedar have, is actually rather non-trivial, okay? Because we have particles and holes that are moving in opposite directions. And in a sense, it's these collisions at the fixed point that actually generate this quantity finite, so that we didn't have a Drude peak. Okay, so basically this can be thought of as interactions rounding out that Drude peak. Okay, it starts to look similar to things that you see in ADS-CFT. Okay, and all of these were kind of controlled by the Epsilon expansion, and the fact that the conductivity is going as 1 over epsilon squared is kind of, it's a kind of very pedestrian way of saying, this is quite a singular type of expansion. Okay, it goes as 1 over epsilon squared. Nonetheless, we're going to kind of be very primitive and at least evaluating it at epsilon equals 1, because that's normally what you do. But somehow it's harking back to this non-trivial process. So I think for a long time people didn't look at thermal effects in these problems, because if you apply temperature gradient, particles, holes move in the same direction, and this mechanism for scattering doesn't apply. Okay? So somehow, the thermal coefficient, the thermal conductivity diverges in the clean case. And so there didn't seem to be very much room for non-trivial transport coefficients, okay? So this is work done with Shivaji Sondhi and Andrew Green, where we tried to look at this then in crossed electric and magnetic fields, okay? So let's think of the following situation. right? I mean, Nernst was temperature gradient looking at electrical response, but we could equally apply an electric field and look at heat flow via the Onsager relations. And you can get some intuition for this problem, okay, by just thinking about behavior in crossed electric and magnetic field, right? I mean, at the end of the day, somehow this is a particle-like picture, so let's just imagine what do particles do if they move in crossed electric and magnetic fields. So one thing you can demonstrate is that particles, one thing that's useful to note is that if you have a Lorentz invariant situation and you run past this system, okay, in a moving frame, then under a Lorentz transformation, you can write the transformation of the electric and magnetic fields in a form that's convenient for what I want to try and extract. This is just straight out of Jackson, okay? Okay, and let's just do it for completeness, okay? Okay, so there's many ways in which you can write down, but this form is particularly useful. What it shows you is that if your electric field is less than c times the magnetic field, you can always move to a frame, okay, moving with the so-called drift velocity, okay, which is E cross B over B squared, right, where the electric field vanishes, right? It says the electric field is less than the magnetic field. You can run into a frame where it vanishes. It then means that your particles only experience a magnetic field, okay? And so if you boost back then to the lab frame, okay, your particles are executing some kind of helical motion, so don't trust me on the sense of these things, okay? But it's something like that with a well-defined drift velocity, okay? Now, one thing I also mentioned, but we never actually managed to get very far, is actually there's also another regime where the electric field is bigger than c times the magnetic field, where you can run into that frame and get rid of the magnetic field, and then you're left with an electric field. And it might be interesting to look at this within the ADS-CFT correspondence, because basically in that regime, in the clean theory, very naively, you've got some runaway motion of the particles, but on the other hand, we know from the work of Subir with Kedder-Daimler that somehow you must be able to tease out some finite results in that regime. Okay? What's more natural when you first look at this problem is this drift regime, because if you imagine you're interested in linear response transport in the presence of a magnetic field, you're going to fix the magnetic field and then send the electric field to zero. Okay? So this is the one to start looking at. And I think there's also a similar kind of regime that comes out in temperature gradients, okay? But it's a little bit harder to argue on the basis of Lorentz transformations, okay? I think one way in which you can probably do it within the framework of the Boltzmann equation is you can actually just look numerically at what the orbits look like for this Boltzmann term and see how they vary as a function of the system parameters, and that I think there's a transition even in the presence of a thermal gradient, okay? Okay, so fine. So let's carry on. So then what it says is, it says, well, okay, look, I mean, you know, we've boosted into this frame, we've killed the electric field, the particles only feel a magnetic field, they therefore don't have their energy affected by that. What it says is that basically we can guess that the Bose distribution function ought to satisfy this Boltzmann equation, or at least you can guess that it might satisfy it in this presence of electric and magnetic fields, okay? So if you use the fact that the energy transforms under a Lorentz transformation like this, okay, then you can speculate that the Bose distribution evaluated on that energy, okay, is a solution of the Boltzmann equation, okay? So let's just write it explicitly, okay? Okay. Now what you can do is, as a result of that, you can say, well, you know, first of all, is it a solution of the Boltzmann equation? And actually it turns out that it is a solution of the Boltzmann equation, okay? So you can explicitly demonstrate that the left-hand side of the Boltzmann equation is 0 when it acts on this, okay? And in a similar way to, in answer to John's question about, you know, if you put, how could you see, first of all, that F0 is a solution? Well, it's e to the minus beta e times the Bose distribution function. So since this involves shifts of the energy and the momentum, it again goes through as a solution even in the presence of the collision term, okay? So what it says is that actually you've managed to guess on the basis of Lorentz transformation arguments what this distribution is in crossed electric and magnetic fields. And so if I substitute that now into the definition of the heat current, okay? So the heat current is very similar to what we wrote down for the electric current, okay? Difference being, of course, that now we're not transporting charge, okay? So it's Vk times epsilon k times the sum of these distribution functions. And if you substitute in this expression, okay, you can Taylor expand in powers of the drift velocity, and you can tease out the linear response result, okay? So let me not go through that analysis. Let me just write out what the answer is, okay? You get an expression for the heat flow, the transverse heat flow that flows in response to an electric field in the other direction, okay, alpha xy, okay, of this form, okay. So I've actually not only computed the the heat current, I've teased out the form of the transport coefficient, okay. So you get this. Okay, now that's fine, that's very good. It turns out there's a very simple interpretation, okay, of this result, okay? Because what you could imagine is that if you've got some particle, okay, that moves under the action of this drift velocity, okay, then it's going to take with it a certain amount of heat energy, okay, which is temperature times the entropy density, okay, and it's going to move at this drift velocity. So let me just skip a few, yeah. Probably. I mean, it's in k dimensions. So yes, ultimately yes. So the reason I haven't done it is good. So the reason I didn't do it is if you do it, you're going to end up doing things that wed you to the epsilon expansion. And so in order to see connections to ADS-CFT, it's better not to get bogged down in all of those numbers yet and just look at the form of that and try and interpret it. Okay, so that's why I didn't do it. Yeah, good. No, that's a good point. So very good. So alpha xy will turn out to have a straightforward interpretation and not depend on the collision term, in contrast to the conductivity. But to kind of preempt what I will say, because we found a non-trivial transverse response, you can look and ask, does it have any feedback on longitudinal response? Okay? And this becomes clearer when we start to look at temperature gradients. And the point is that if you look at the problem for a temperature gradient, okay, there should be associated with that temperature gradient a transverse electrical current. But then as a result of that transverse component, when you go back and look at the Boltzmann equation as a coupled system, it means you've also developed a longitudinal thermal conductivity in a magnetic field. That turns out to depend as epsilon squared. So it's reciprocally related to the conductivity that you get, very non-Wiedemann-Franz law, okay? And I'll come back to that in a minute when I discuss the ADS-CFT results. So, okay, so what is the meaning of this, right? So the meaning is that, was there a question? Sorry. Yeah.
Is this expression not zero?
Is it what, sorry?
Is this expression not zero? I mean,
No, it's k squared. Sorry, I might have written that. No, it's a derivative with respect to epsilon k. It's a Bose function, yeah. I don't think it's zero. So, no. Okay. Okay, so fine. So let's just imagine then that you want to try and guess the answer, right? So what's the point? So the heat flow is the amount of heat that's transported, which is temperature times the entropy density, okay? We have two species of particles, so this is the entropy density of a complex particle, okay, two species, okay, we'll come back to precisely what it is in a minute, but it's something to do with entropy density times this drift velocity, okay, which is E cross B over B squared, okay, so then if I get rid of the B, okay, this is proportional to the electric field. If I look at the coefficient, okay, it says that this should be temperature times entropy density divided by a magnetic field, okay. So this actually isn't the first time this result's come out. It's cropped up in different places. I mean, it was the first time it had come out in relation to transport near a critical point, okay? But actually, if you take this answer and try and interpret it, it turns out that if you take the entropy density of a charged scalar field and substitute it into that formula, you get out this answer, okay? And so this is also the answer you get out from ADS-CFT, okay? What's a bit more striking is, as I said, what we were interested in is not just looking at this in relation to electric and magnetic fields, but looking at what happens in a temperature gradient. So let me just try and summarize that. So how long have I got? 15 minutes. Okay, so I'll just wrap up in 5 or 10. So, okay. Okay. So what do we want to do? Well, we want to impose a temperature gradient, okay? And so one way in which you can do that is to, sorry, that's an X. Okay, so basically what you can do is you can assume that the only spatial inhomogeneity comes from the temperature gradient that you apply, and so you can, just with a little bit of minor fiddling with derivatives, you can express this as okay. And I should say that because we're doing linear response, okay, I've replaced that with the Bose distribution function, okay, because it's already proportional to the gradient of temperature, okay. So basically just assume that you have some distribution that varies its position, but the only reason it does so is because you put a temperature gradient. You can recast that in a form that brings in the temperature gradient explicitly, okay. And so then what you want to do is you want to solve the resulting Boltzmann equation, okay, by a linearization again, okay. Right, and it looks similar to what we wrote down before, okay, but with a slight change because particles and holes move in the same direction under the action of the thermal gradient. So there's no plus or minus here, but they pick plus or minuses up when you look at the transverse response, okay? So U, I should say, I've defined as minus grad T, oops, over T. So it's just saying, look, I mean, we've got some longitudinal shift because of the temperature gradient. We're in cross temperature gradient and magnetic field, so there's also a transverse shift. And what you want to do is you want to write down the resulting linearized Boltzmann equation that includes both of these terms, okay? And I think given the time, I'll spare you the details of it. Basically, you know, it's straightforward. You substitute this in, you linearize in the temperature gradients. You're going to pick up two collision terms now, both from the longitudinal and the transverse response, and you're going to try and solve this equation within the epsilon expansion, okay? So if you do that to lowest order, okay, what you find is that there is no longitudinal shift, okay? And then actually this transverse distribution that you compute, right, ends up reproducing your answer you got from electric and magnetic fields. Okay? But now there's something interesting, which is because you've got this transverse distribution, and it's a solution to epsilon, order epsilon to the 0, if you substitute it into the full linearized equations again, you find that at higher order, you generate a non-vanishing longitudinal distribution. Okay? And so we computed that, okay, and again, I'll spare you the details, okay? But the upshot is, if you take that longitudinal shift and you ask what is the resulting heat flow, we managed to tease out a formula that looks as follows, okay? So it's not particularly illuminating at this stage, okay? Okay, and there's some value, right, which computed was this, okay, at least in the letter. Okay? So there's some thermal conductivity that goes as temperature to the d plus 3, it goes as 1 over b squared. Rather crucially, it goes proportional to epsilon squared, so somehow it's going like inverse sigma, right? This is q squared on the bottom, it's going as inverse sigma, and there's this factor of g, okay? And so then this is where all the nice aspects with ADS-CFT come in, right? So let me turn this on. Is it okay to leave it? Okay. Okay. So this is the result that comes out of a holographic calculation and also using supersymmetric Yang-Mills theory, and also relativistic hydrodynamics in 2+1 dimensions. Right? It says that the thermal conductivity in a magnetic field is given by temperature times entropy density squared divided by sigma xx in 0 field divided by b squared. Okay? So in contrast to the usual form of the thermal conductivity where it goes proportional to sigma, this goes inversely to sigma. Okay? Now if you look at the answer that we had before, right, it went as t to the 5, okay, and in in 2+1 dimensions, entropy goes as t squared, okay, so it's going as t to the 5. We had all the ingredients for sigma xx, and then the question comes down to this coefficient in the front. And if you work it out, it differed by 20%, okay? And so there's a subtlety, right? So first of all, you might worry and think, well, hang on, can this epsilon expansion even make contact with these results? These are results done directly in 2+1 dimensions. It's very cute. It'd be very audacious to assume that such a duality relation existed just simply because it was reciprocally related. I mean, you could obviously unpack it in terms of the conductivity, but getting that number is precisely unity, okay? So the subtlety is that actually what we did in solving that Boltzmann equation was just very straightforward. We said, look, we've computed this transverse response by 5 different methods. If you back substitute that into the coupled equations, there has to be a corresponding linear response, okay? And that's what we computed. However, if you look at the form of those coupled equations, okay, they actually contain a parameter that depends on the magnetic field squared divided by epsilon to the 4th, okay? So it looks a bit strange, okay? What this is basically saying is, in much the same way that there was a crossover between a collisionless regime and a collision-dominated regime within the frequency-dependent conductivity, here the issue is that you're in a finite magnetic field, okay, so your particles are executing some cyclotron orbits, and what you want to make sure is the particles experience a lot of collisions during the time period of a typical thermal carrier executing a cyclotron orbit. So to get into the hydrodynamic regime, even though epsilon is small and you're using it as a control parameter, you've got to be careful because it's shifting you out on this axis. So that the dimensionless prefactor we computed. Yeah, sorry? Sorry, so this is, sorry, it's very small, isn't it? This is this coefficient that we call G, okay? So in our work, there is just so many factors that are related to how we define things. But there's a dimensionless number that we computed that was 5.5, okay? And if you look at how it runs basically as a function of the magnetic field in the problem, then the point is to get the hydrodynamic result here, okay, this value of 4.66 actually corresponds, when you substitute it in, to this self-dual expression that you get out of ADS-CFT, okay? So there's a kind of, you know, it's a dimensionless coupling that you have to track into the hydrodynamic regime. And in fact, what you can demonstrate analytically in this Boltzmann framework is that the collision term is dominated by particular zero modes. And in fact, we were actually led to try and understand this, but also from some work of Subir and Marcus Muller, because a very similar situation arises in graphene, where things run involving the fine structure constant associated with graphene, okay? So the point I just want to emphasize is that there is a direct communication between the results that you get out of standard approaches to quantum field theory for these critical points and results that come out of ADS-CFT, okay? But the point is, within ADS-CFT, you can really start to compute things, right? Because you're not bogged down by these specific forms of the collision terms, et cetera, et cetera. And so this was just stolen from Sean and Subir's paper, okay? So here, they're also including the effect of impurities, okay? So one of the things I said is we started off just looking at the clean case, so just send tau to infinity in this formula, okay? So then that's going to drop out. So you see, indeed, alpha xy is going like entropy density divided by the magnetic field, okay? But now the point is that if you start to look at the Nernst coefficient, you can also look at this in finite chemical potential, and then what you see is that indeed, if you go back to the clean particle limit, it diverges, as I said it would, because it goes divided by sigma xx. But the point is that to tease such results out of that Boltzmann equation would have been an absolute headache. Okay. Now, I'm sure it's probably possible, and maybe with the benefit of hindsight, there's now simpler ways to look at that Boltzmann equation, because you see that somehow the structure of the collision term has to respect certain zero modes to enable you to make contact with hydrodynamics. So I take this as being, a very useful sign that you can use ADS-CFT methods in condensed matter contexts. It's not going to be helpful, as I said, for working out this value of sigma xx, that's specific to the model, but the fact that all of these transport coefficients are actually related, this was just one example, okay, of a whole slew of relations that they derived that show that this is essentially the only quantity determining the transport coefficients, and everything else is thermodynamic variables. And I think that's not obvious in any kind of condensed matter treatment, okay? At least not to my understanding. So I'll leave it at that. Yeah.
In the absence of any quasi-particle picture, does the Boltzmann transport method is working still?
Sorry, in relation to which method? There is no
quasi-particle picture due to this strong dimension.
Yeah, so well, the question is, how do you write it down and control it? Okay, so here, within the framework of the Epsilon expansion applied to lambda phi to the 4, then there was a controlled expansion for which you could go about setting up a Boltzmann-like equation. Okay? Now, if you're in a very strongly coupled regime, you might not even be able to start to think about such things. On the other hand, I do know that there are papers related to the relativistic Boltzmann equation in relation to the quark-gluon plasma. Okay, so there's papers by, I think, Blazot, I don't know how to pronounce the name, B-L-A-I-Z-O-T. And actually, in some sense, they were actually quite instructive in just understanding general properties of relativistic Boltzmann equations. But I don't know how quantitatively they will be able to handle that strongly coupled regime.
Your question is whether it is meaningful to compare it to some result of the Boltzmann and the ADS. Because the ADS is intrinsically strongly coupled.
Well, but I think the point I tried to make is that we did these computations using the Boltzmann approach, And you see that actually it's quite tricky to analyze these equations numerically, and that calculations done within a strong coupling regime enable you to grasp that there's certain relationships between the transport coefficients that are in fact just consequences of hydrodynamics, and therefore both the weakly coupled approach and the strongly coupled approach, provided you work in a hydrodynamic regime, must talk to each other, okay? And so in that sense, the ADS-CFT results were actually useful to go back and try to understand direct field theory type, I mean, not field theory computation, I mean, this is Boltzmann transport computation, but, you know, field theory inspired Boltzmann calculations. So I think there is a sense in which you know, compare is not quite the right word. I would say inform might be a slightly better word, right?
Maybe if I can comment.
Yeah.
So what he's shown is that at small epsilon, certainly this is the first PV results. It gives you these relations between transport coefficients that are consistent with ADS-CFT and also hydrodynamics. But it is not at all clear whether the value of sigma 0 at can be trusted at epsilon equals 1. And furthermore, what happens at higher frequencies? So I'll discuss it a bit in my second lecture. But there's latest numerical results on this particular field theory. It's clear that this 1.037 is quite far from the actual answer.
So done numerically within Bose-Hubbard?
Well, it's the rotor model, but not the Bose-Hubbard.
But done numerically, sorry.
That's right, yeah.
Okay,
yeah,
so there's a kind of an exact, in quotes, result for what it is in the model. And
This is what
okay.
we didn't talk about.
Okay, fine, okay, good. Yeah, so you see, but the thing is that that's why I was saying I wouldn't necessarily, I mean, the dimensionless numbers are obviously interesting, right? But they're computed for a specific model, right? So if you want to compare to ADS-CFT, comparing that number isn't going to be so helpful. But knowing that there's links between transport coefficients that are consequences of more general aspects of hydrodynamics, that's very useful, okay? So, you know, if you do an epsilon expansion in any model, right, unless you do something like Borel summation or whatever, you know, you might not necessarily trust the answer you get out if you just do a lowest order computation, okay? But